recording. All right, this is a chat window. Let me make it larger. And here are the participants. So let's wait a couple of minutes. We should have at least like 25 or so students. All right. So today we are going to start our first algorithm on ray tracing, which is going to be, we're going to first look at its geometry. And I'm going to describe the basic algorithm. So it's a really simple algorithm, but we will be able to generate very nice looking images with this algorithm. And you're going to also understand why it is very time consuming to generate images using ray tracing. We need to have lots of optimizations, parallelizations to make it faster, to make it real time. In the context of this course, we are not going to focus on this parallelization or indexing the scene for faster intersection tests. Instead, we are going to just describe you the basic algorithm, and when you implement it, you will have probably, a complex scene will take minutes maybe to generate a single image. All right, so yeah, we have 25 participants. So as usual, if you have any questions, please feel free to interrupt me anytime, either by unmuting yourself, or you can write in the chat box if you have any questions. I will be constantly checking the chat box during the lecture. And so yeah, let's start. So what's ray tracing? What do we want to do? If you remember, our goal, let me start the slides. All right, so our goal in graphics is to get a 2D image, to take a photograph of a three-dimensional scene. So the scene is, for example, this is a very simple scene with a single sphere. In order to be able to take a picture of this sphere, this figure from Wikipedia shows the all of the important actors that we need, inputs, in order to have the picture of the sphere on this 2D image. So let's first take a look at these components. First of all, I need to have an object to be able to see something, all right? The sphere. In order to represent this sphere, so this is a virtual three-dimensional world. We need a three-dimensional coordinate system. So there should be, at some place, there should be some world origin. Maybe this is the x-axis, and this is maybe the y-axis, and maybe this is the z-axis, positive z-axis. So this is a right-handed coordinate system. All right, the way I drew it like this. Maybe this here is 0, 0, 0, and based on this global coordinate system, or what we call the world coordinate system, this sphere will be represented in some manner with some data. What do we need to represent the sphere in these 3 dimensions? We need to know its location of its center. Let's call it C. C is a vector here composed of x, y, z coordinates. So we need its center. We need its radius, r. Okay, so it's really simple to represent the sphere object actually in our virtual world. All I need is to have its location of its center and the radius the sphere contains. What other things I can need about this sphere? For example, its color. All right, this is like a yellowish sphere. I need its color. How shiny it is. What material does it have? We are going to use this material information to implement, for example, whether there are shiny spots in order to find the compute the color on a point on this sphere, the material properties will be taken into account. So, okay, this is how we represent the sphere. That's our virtual world, but it's not enough. We need, in order to be able to see something, even you may have a yellow sphere in the scene, but when there is no light, it will be completely dark. So what makes things seeable is basically light sources in the scene. So we need a light source. That's another thing. How do I represent this light source in the scene? It may also have, let's call it L, it may have a position. Okay, the light source may have an XYZ position in the scene. The light source may be omnidirectional. It may be a point light source which emits light in every direction. It may be a directional light source which emits light in only this direction. All right, or it may be a spotlight. So it may be a spotlight in which only objects that are within a certain cone will be illuminated by this light source. So there may be different parameters of the light source, but what we need is this position, whether it's a point light or not. We are going to come to those later, but for simplicity, just assume at the first, in order to understand the basic ray tracing algorithm best, just think about a point light source which is omnidirectional. So if I have an object here, this light source will also illuminate that. If I have another object, so it's basically just consider a point which just illuminates light in every direction around it in a sphere. Okay, in a spherical manner. Now, okay, we have the light source, we have the scene object. So the way actually this snapshot is taken, we are looking at the scene from a certain perspective, from a certain direction. The last important parameter that we need to think about is, where are we going to take this image from? Where is the eye point? Where is the camera? So our camera model in ray tracing, and also that is used in OpenGL as well, is a camera model that looks like this. So there is a camera. Actually, the camera, this picture is a little bit misleading because this entire thing here will be considered as the camera, because this image here that is in front of the camera is the image plane of the camera, and we are going to be generating images on the pixels on this image plane, which has a certain boundary, left boundary, right boundary. By the way, I call this left because I'm looking at this image from the perspective of the camera. So just think about, if you were at the camera and looking at this image plane, this will be your left boundary. This will be your right boundary if you're looking at this direction. And this is the top boundary, and this is the bottom boundary. So the image, there's an image plane which is infinite in front of the camera, and on the image plane there is a bounded region which we call the image. What we call camera here is actually the focal point in which all the light rays coming into our camera are focused on. There is they converge on this single point, and the way we are going to perform perspective vision is we are going to just collect these light rays. In reality, what happens in real cameras is that light rays are hitting on this image plane from every direction, and they're collected and accumulated on the sensors on this. Usually on a real camera, there are sensors at these pixels, and they collect light that is coming accumulated at these. Okay, so by the way, I'm going to erase these. It's just seems like a child's drawing, so I'm just, and I drew lots of things. I'm going to just erase the things that I draw on the board, and I'm going to start new. So what we are going to have is that instead of collecting light rays coming from the objects on these, we are going to do a backward process. Okay, we are going to trace the light that has come into this sensor in a certain direction by tracing the ray backwards. So that's why the algorithm is called ray tracing. We are going to start a ray from the focal point in this direction towards every pixel. Just think about this pixel. The center of the pixel will be considered as a very tiny small pinhole, a small hole that light can pass through. Therefore, only lights that come in a certain direction will be considered. Hence, we are going to have sharp images. That's actually that pinhole camera idea was used in the early cameras at the end of 19th century. They had maybe in the middle of 18th. I don't actually know the history of photography that much, but there's something called pinhole camera, in which lights that enter that pinhole only in a specific direction enter the box. You have a dark black box, and you just put a pinhole with a pin. You just punch a hole in that box, and with that you can have sharp images. Otherwise, if you have a larger hole in that box, a light rays coming from every direction will fall in the same image that you're in the same image position, then it's going to accumulate, and you will have blurry images. The way blurring occurs is that, for example, you have a certain position of an object, a sphere. Light rays coming from this object may hit. We want this point to be visible in only one location on the image. If it just disperses to some surrounding pixels, we will get this blurring effect. So let's not lose focus here. What we are trying to do is actually to simulate that pinhole camera for every one of those pixels, and we will be only interested in rays that are shown here. That, for example, the ray that passes through the center of this pixel originating from this camera. We will be tracing this ray, and we will be asking this question: what object does this ray see in the real world? In other words, which light reflecting from which part of the object? Which part of the object and which color of light in this direction? We are not considering light rays coming in different directions to this pinhole. We will be only focusing on this one. All right. Therefore, let me erase them again. And therefore, this will be our only single ray of focus when we are considering a single pixel. So the ray tracing algorithm is very simple in the sense that it treats all of the pixels separately. The overall ray tracing algorithm, there is a main loop at the main function at the top, which says for every pixel in your image. For every pixel, do this. And what you do for every pixel is going to be the same. We will be generating from the focal point to that pixel center. Yeah, we have the same image here. So we are going to generate these rays and ask this question: what does this ray see? In other words, if I had a tiny window at the center of this pixel and I was looking at this direction, at this focal point, what would you see? And if this hole is really, really tiny, you will be only seeing the closest object. It's like you have zoomed in an infinitely small region of your scene, and you're only seeing the single point in the scene. This center of the pixel is really infinitesimally small. Yeah. Yeah, I'm recording the session, so you will be able to watch this later with the whole 180 resolution and better sound, I guess, this time. So yeah, I have a new microphone. I hope it's better than the microphone of this thing. I'm not using this one anymore, but let's see. The recording also important. The recording sampling rate. The OBS has 48 kilohertz maximum. I'm not sure. I think it will be sufficient. So yeah, just think about a very tiny window. You will be able to see only a point on the real world, and we will be interested in this question: what does this ray see? And if we will first find the object that it sees, and then we will ask the question: okay, what color do we see? Okay, you said it's a yellow sphere, but is it at this point? Am I seeing a darker yellow or a brighter yellow? For example, this ray. Considering the light source, for example, if you look at the sphere, it looks three-dimensional because certain parts, it's shaded. It looks three-dimensional because it's shaded, right? Shaded means certain parts are darker yellow, certain parts are brighter yellow. So this gives it a three-dimensional feeling, because with respect to the light source here, surface points that are directly looking at the light source should appear brighter. This is the physics of light rays interaction with the sphere. All right, now, yeah, this is basically the whole ray tracing algorithm. We will be asking we will first answer the question which object we are intersecting with. So I have a cat here and I'm trying to shoo her away. Okay, yeah, she's gone. Now, yeah, we are first going to, it's really with mathematics we will find the objects that we intersect with, and then by some vector computations we are going to also figure out whether yeah, I can actually use the cat as an object. That's a good idea. Yeah, if she comes again, I will do that. All right. Now, okay, let's start. Let's try to solve this problem. If I give you a sphere like this, if I give you as a C programming problem, I have a sphere at, for example, 3, 4, 5. At coordinates 3, 4, 5, I have a sphere with radius 1. I have a camera at this location. I will give you the coordinates. For example, it says 0, or it's -5, -5, -5. And is the camera, what about the camera? Actually, we haven't talked about that. We have talked about the light source, its parameters, and I just talked about the camera like this. But how do we define a camera? We are going to be using the coordinates of the focal point, and also things like the distance of the image plane to the focal point, because that determines our field of view. The boundaries, left boundary, right boundary, top and bottom boundaries of the boundary image, the distance of this focal point to the image. Also, we are going to assume the camera is looking in a direction which is orthogonal to the image plane. We are going to assume the angle here, then the looking direction of the camera is 90 degrees. Okay, so this is not necessarily so. We may have cameras in which the image plane is at an oblique angle to the camera, and we are not going to, for simplicity, again, just assume the simplest setting. The camera is looking directly at the image plane at the 90-degree angle, and also the camera's gaze. The camera, because it's a point, the camera's focal point, our focal point will be a single point, and our gaze will be a single vector, a direction. And this gaze, we are going to assume it hits the middle point of our image plane. All right, so we may actually have images in which our gaze is like this, and we may be looking, I mean, the angle may be 90 degrees, but imagine an image that is like this. Okay, twice as longer, the width is twice as larger, the camera is here, the gaze is hitting not the center of the image, but at some other point, pixel on the image. This may be possible. All right, so but again, for this, at the simplest setting, let's assume our camera is looking at an image plane, the left-right boundaries. I mean, this basically will assume that the left and right boundaries, the distance from the left boundary to the center, the distance of the right boundary to the center, are equal. These will be equal, the same for top and bottom. And we are not going to assume a square image. We are going to assume we may have any rectangular image that we have. In other words, top and bottom, this distance from the center to the top may not be equal to the distance from the center to the left or right. All right, so we are going to have, I'm going to describe some example settings, some real values. But if I give you this as a problem like this, how do you take this picture? How do you take a photo of the scene with this camera? The ray tracing algorithm will do this. For every pixel on this image, generate the ray. Find the closest object that this ray intersects with, and set the pixel color to the color of that object. It's that simple. All right, so it's a really simple algorithm. Do this for every pixel. If you have 1 million pixels, run your loop 1 million times, and for every iteration of your loop, find the ray, first we are going to, our first part of the ray tracing algorithm will be, how are we going to compute a ray? What are these rays? What are the vectors of these rays? Given what will be the input to me? The pixel coordinate. If I give you, for example, pixel coordinate 0, 0, this is, for example, our 0, 0 pixel. If pixel coordinate is 0, 0, what is this ray equation in 3 dimensions? That will be our first problem. We will construct this ray equation. After you have your ray equation, which is like a line equation actually in 3 dimensions, the next step will be, okay, this ray, which object does it intersect with? Potentially it may not be intersecting with any object. In that case, the pixel color will be what? The background color. So if we don't see anything, if in the virtual world we do not see anything, if our ray does not hit anything, what we will be doing is we will just be assigning the background color to this pixel. It may be black, it may be white. How does it determine when it doesn't hit anything? It's simply be like this. We are going to intersect this ray with all the objects in the scene one by one. So we are also going to see a line sphere intersection. The mathematics of this will be, we need to have an equation that tells us, given a ray, 3D ray, does it intersect with a sphere? The answer will be 3 of the things. It may intersect the sphere at a point. In that case, the ray will be tangent to that sphere. It may intersect the sphere at 2 points, all right? Or it may not intersect the sphere at all. Okay, so, and we will be, after going over all of the objects, if your ray doesn't intersect with any of the objects in your scene, it means that it doesn't intersect with anything, and you can assign background color to that one. There is no boundaries. We will not have boundary space. So you can also do that. I mean, you can have a bounding box, and that bounding box will not actually be different than another object in your scene. We will see, in addition to spheres, we will be able to compose a scene composed entirely of triangles. So the objects that we will be seeing in this ray tracing algorithm will be spheres and triangles. Those are going to be basic primitive objects, and we will, if you know a function will be given a ray and given an object. This may be a sphere, this may be a triangle. Find whether they intersect or not. If they do, also give me the intersection point. So our basic function will be this, and we will be able to generate very complicated scenes. The horse and mug scene that I showed you earlier, with a small statue, silver horse, and a white mug next to it. That scene was composed entirely of triangles and spheres. All right, so this is what we are going to be doing. And in ray tracing, we will not have a bounding box in ray tracing in general. So the other question, if you want to make the camera a fisheye, yeah, we sometimes curve the image plane. We don't have rectangular image plane, but we can also do a fisheye rendering with not a curved, with a planar image. But if that image is very close to the camera, you will also have a fisheye effect. You will be able to see field of view which is really large, close to 180 degrees. By the way, at 180 degrees, if this image plane is exactly at the camera, that doesn't actually, that's a singularity. Okay, we will not be able to generate any rays. So the smallest angle field of view you can have in X or Y directions should be less than 180 degrees. 180 degrees is a singularity that we will not be able to. So if you want to have fisheye camera, you can have the angle, field of view angle, as close as possible to 180 degrees, but not exactly 180 degrees. Okay, yeah, that's a very good questions coming up. So will we reflect the ray when it touch an object? That's a very good point. This is how we are going to get reflections of other objects. For example, things like this. Let me again erase this slide and come back to it again. All right, so look at this ray. We'll be asking, okay, this ray sees this point on the object. Okay, when we ask the question, what is the color of this point? Okay, look at this ray. This ray sees this point on the object. The next thing we will be computing is, what color is this point, or which is the same as saying what color is this ray, what color does it see. It depends on lots of things. For example, the position of the light source with respect to this point, or for example, if this is like a mirror-like surface, meaning that there's a tiny image that may be formed here. What if there's another sphere here, and the lights that are bouncing off from this, maybe this is a blue sphere, doesn't look. So if there's a blue sphere here, let's let this be blue sphere, light rays bouncing off this blue sphere may also be hitting the same spot. All right, so and if this is like a mirror, like reflective object, the reflection of the blue sphere should also be seen at this point. All right, and also what if there's another object that is blocking this light rays coming onto this point? What will we have at that point? We will have shadows. Okay, so this shadow ray that is shown here is we will be generating this shadow ray, and if there's another object that this shadow ray intersects with, and if this intersection is before coming to the light source, I mean there may be another object behind the light source, if this shadow ray intersects with that object, it doesn't cast any shadow. In order for an object to cast a shadow, the intersection should be between the light source and the object point, and we will be doing this. I mean, it's really very nice to see. I mean, you will be writing code with if statements and calling your ray object intersection functions and checking this, and with this implementation of a function, you will immediately have shadows on your images. So the effect will be really visual, and it will be something really appealing, because shadows are really important clues in our vision about the scene. So it will make the quality of the generated images a lot. I mean, if you have shadows in the scene. Yeah, objects may be made of transparent materials. We will not talk about transparency in this course. If they're transparent, for example, you will have to maybe reflect some part of the ray and maybe refract. Okay, refraction. Let me write this on the chat box. The light ray maybe is going to pass through the object, and we will be not only reflecting rays, but refracting rays should also be considered if you have transparent objects. And ray tracing is able to handle transparent objects as well. Okay, it's just physics. You're just going to create another ray equation depending on the refraction coefficient, and you are going to follow that ray. And you may be also asking, what about this blue sphere? Is this point really blue? What if there is a green sphere in which its reflection is also here? So all light is bouncing off every object in the scene. So usually we are going to trace this ray back to a certain number of steps, because these are time-consuming computations. Computing the ray, finding is the most time-consuming part. One of the most time-consuming part is finding the intersection of a ray with the scene objects. If your scene is not organized in a nice data structure, the only thing that you can do is, given a ray, intersect this ray with all of the objects in your scene one by one. All right. Finding it, especially let's think about the first ray. Look at this ray. There may be lots of objects in my scene. Okay. Now, and they may be organized. They may not be organized in a data structure. And if I say, for example, find the intersection of this ray with the scene objects, and starting with object 1. This may be object 1, object 2, object 3, object 4. Okay. As soon as you find an intersection, should you stop intersection tests? In the problem of the first ray, I mean this one, no. You should actually intersect this ray with all the objects that are on the line of that are on this line, because we are interested in the closest object that we see. Or for example, this ray intersects object 2 as well. But if we find the intersection of the object 2 with the ray first, it doesn't mean that this ray sees object 2. It's actually seeing object 4 because it's closer to that. All right, therefore, we need to intersect the ray with all of the seen objects, and among the intersections, we need to keep the closest intersection, because the closest intersecting object, if there is another triangle here, for example, the ray will be seeing that triangle. Of course, this is in the case of non-transparent, opaque objects. If you have transparent objects, everything changes. You need to take into account refraction. There may be objects behind objects, may be seen. They will be accumulating in the color in the ray that we see. These are really advanced things. Just do not think about that too much detail when you're thinking about the ray tracing algorithm first. Just think about, we have all opaque objects, no transparency at all. We're just going to shoot this ray, follow it maybe 2 steps at most, and then accumulate color based on the light source and the other objects, and we are going to then assign a color to this pixel. That's it. After you assign a color to this pixel is done. Do this for all the remaining pixels. And when you have all these 1 million pixels, what do you have? You have a photo, or you have a picture of your virtual scene. Okay. Yeah, so that's yeah, if there's another object in the front, the answer was correct. You have to continue looking at all the intersections. So a very important part in ray tracing is, okay, I should not have my virtual scene unorganized like this. I should have an index structure, like oak trees, BSP trees. I need to have some kind of a binary search or bounding volume hierarchy. For example, imagine you have hierarchically group your objects so that they're inside boxes like these. Okay, you have large boxes that you use. You first intersect your ray with these large boxes. For example, if this ray does not intersect with this large box, what does it mean? It doesn't intersect with any of the tiny smaller objects that are inside the box. So that's one. We are going to come to that later, but you're not going to be implementing this. I think it was in the previous year's homeworks. This bounding volume hierarchy was something optional. That was a bonus to speed up your ray tracing code. Some groups did that. Some groups implemented this bounding volume hierarchy, and it sped up the ray tracing algorithm tremendously. A code that was running 10 minutes run in seconds after this, indexing your scene to have a more efficient intersection test. Okay, so yeah, this is the overall ray tracing algorithm. As you can see, it's simple, but now we will go into the mathematics, so that, I mean, at a high level it's simple to understand, but when you come to implement it, you need to have some simple vector algebra. You need to, how do you generate a ray? How do you do intersection tests? How do you compute the shading of the color on that spot? But yeah, when an object has a lot of triangles, we treat all of these triangles as separate objects themselves, and we intersect the ray with all of the triangles. So if your scene contains 100,000 triangles, without any indexing of your scene, you have to intersect your ray, single ray, with 100,000 triangles one by one. That's why it's really, the basic algorithm is very time consuming. This is for single ray. Intersect a single ray with 100,000 triangles, and you have 1 million such rays. If you, I'm using this 1 million repeatedly. A 1 million is for a 1 megapixel image. Okay, if you're going to have a 1 megapixel image, for example, 1000 by 1000 resolution, 1 megapixel image, basically, yeah, a 720p a resolution is closely corresponds to 1 megapixel image. It means that you have 1 million rays. Yeah, so let's continue with the first equation. How do we generate ray for a given pixel? All right, let's continue. So this is the camera. I talked about camera, object, light sources, and lots of rays. Now, the camera, the aperture, ISO, shutter speed, frame rate, we are not going to talk about them in this course. We will not have those parameters. The only parameter that we will be adjusting is like zooming in and out. We will be adjusting the distance of the image plane to the focal point. So it's like you will be zooming in and out. The things like ISO, for example, the amount of light that is collected at a pixel, we will not consider those things. Yeah, I think what I'm saying, the adjustable is aperture, maybe, but I'm not familiar with this photography that much, so I may be misleading you. But we will not consider these real camera parameters. Our camera will be a virtual camera in which the focal point is behind the image plane. In reality, it's actually in front. Therefore, the image that is formed actually is reversed. But in order to have so in reality, if this is the focal point, usually if the light rays are coming in this direction, the image is here. Therefore, at this part of the if the image is behind the focal point and the light rays are coming from this direction, they will the image will be reversed. But in order to avoid that, we are going to have a camera which is like a virtual camera in which the image plane is in front of the focal point, just as in the slide that I show you. Therefore, we are going to have straight up images, not reversed, and it will be a perspective vision. Yeah. And another question, yeah, we are not going to, in ray tracing, we will be tracing the rays from the focal point. That's what is called backward algorithm. There will be in the second part of the course where we'll talk about the forward rendering pipeline. In the forward rendering pipeline, we will be tracing the light rays from the objects to the focal point. So they are in reverse order. So ray tracing, so this is something we do virtually. We are free to do that. We will start our rays as if the focal point is the light source, but actually we will be tracing towards the light source, basically. Yeah. The rays will be originating from the focal point, and it's only possible virtually, as you said. Okay, so here's the camera. In order to represent the camera, the camera's focal point. Let's call this not the camera, because camera is a box containing the image also, the image plane also. So this is the focal point. We are going to represent the focal point with a position. Basically this is a vector E. E is a vector here that shows the position of the focal points of the camera in the world coordinate system. Okay, so this E will be, for example, if it's 3, 3, 3, 3, it's a three-dimensional vector with x, y, z coordinates. If it's 3, 3, 3, for example, at some place there is some coordinate system x, y, z. Okay, x, z, and y. I'm looking at this from this side, so we will have a coordinate system like this. Maybe, by the way, this may not be 3, 3, 3 if I draw it like that. The z coordinate seems more like 0 at this point, and x seems to be much larger than the y coordinate value. But what I'm saying is that there will be some coordinate system in which this 3, 3, 3 I position will correspond to a specific point on that world coordinate system. That's our virtual world. It has to have a coordinate system. And in that coordinate system, these directions, this is the local reference frame of our camera, which shows the orientation of the camera. Okay, these U, V, and W vectors. Actually, U usually is considered as the vector 1, 0, 0, a unit vector along the x-axis. But this 1, 0, 0 will be in the local coordinate system of the camera. It's 1, 0, 0. In the world coordinate system, as you can see, this U is just a vector that is something like it's pointing at minus. Look at this U. It seems like the x coordinates. It's maybe something like 1, minus 1, and minus 2. Look at this. 1, minus 2, minus 2 will not. U will be a vector like this, which will indicate the direction. Okay, of the camera from left to right. It will U vector will tell me how the rows are aligned. The rows on the image, the rows of the pixels are aligned on the image. By the way, how we're doing on time? So we still have 10 minutes. Okay, so U vector is going to show the left to right direction of pixels on the image plane. And it may be something, an arbitrary vector like 1, -1, -2, which means that with respect to the world coordinate system, we are not directly looking at minus z direction. Oh, by the way, when we have this, so this is the left to right. U vector will indicate the left to right orientation of your pixels. It's the x-axis of the image. And v vector is the y-axis of the image. It's going to tell the orientation of a column on your image plane. Okay, so basically u and v are orthogonal. So this u, v, and w, they're all orthogonal to each other. These are pixels in your rows, pixels in your columns, that direction. Your pixels, in order to have a nice rectangular image, those pixels also have to be orthogonal to each other. Okay, so this is the up. This v is sometimes called the up vector of your camera. For example, when you have a real camera like this, all right, so if you move your camera like this, as you can see, the up vector is tilted. Okay, or you can move the up vector like this. So this is the up vector. This is v. My index finger is showing the up vector, and so this is the up vector. You can, if you move it like this, you will have a tilted image. Okay, so this is the things that you move about the camera. And this is the u vector. U vector is this direction. Okay, if the v is this, u will be this in the right-handed coordinate system. As it shows, as you can see, the rows of pixels here. And this w shows the reverse of the gaze. So if w is like this, we will assume we are looking, if this is the focal point, we will assume we are looking at the minus w direction. Okay, so minus w is the direction that we are looking. All right, that's minus w, sometimes indicated as the vector g, which is the shorthand for gaze. Gaze is our looking direction. It's a vector by itself. And if, for example, you are given u and v is given to you, if somebody gives you just u and v, gaze will be easy to compute, or w will be easy to compute, because they're all orthogonal to each other. For example, if somebody gives you u and v, what is w? W simply is u cross product. Sorry, yeah, exactly. U cross product v. Just I wrote it in chat box. This x corresponds to cross product. U cross product v. If you do u cross product v and with your right hand rule trace the angle from the u vector to the v vector, you'll see that you get the w vector. All right, and by convention, this is by convention, we assume this is true in OpenGL as well. If we are in a coordinate system, we will assume that our looking direction is this minus w vector. Okay, our gazes in the given a camera like this, we are looking in the minus w direction. All right, so another thing that I need here is, yeah, the position and orientation. These are all given to the global coordinate system, and the global coordinate system, its origin is always 0, 0, 0. X-axis is this 1, 0, 0 vector, y-axis is 0, 1, 0 vector, and the z-axis is 0, 0, 1 vector. In the direction, for example, if I ask you in this global coordinate system, what is this vector in this z direction, you are going to say it's 0, 0, 1. And therefore, I wrote this u vector as 1, -1, -2, approximately, of course, by looking at my global coordinate system. Why did I say 1? Because it seems a little bit in this x direction. If you look at this direction, it's a little bit this way, just a little bit. It's a lot of this way. It's a lot of in the minus z direction. That's why I gave it -2. I could have given it -5 as well in order to indicate. By the way, as you can see, this vector 1, -1, -2 is not a unit vector. When usually when these vectors are given to us, they are given as unit vectors, meaning that their lengths should be actually 1. So if I'm going to indicate u as a unit vector, what should I do? I should divide it by its length. What is its length? 1 + 1 + 4, it's 6. So square root of 6. So if you multiply all these coordinates by square root of 6 and minus 2 divided by square root of 6, you have the same u vector in the same direction, but this time its length is 1. We call such vectors normalized vectors. Okay, it's a normal vector. So yeah, this is what I told you. If you cross product u with v, you will get the w vector, or you can also get u by cross producting v with w. If you cross product v with w, you get the u vector. So if any two of those vectors are given to you, you will be able to find the other. Okay, now we are not done with the camera yet. The other thing that we are going to be talking about with respect to camera is this image in front of the camera. Now, so if we are looking in this direction, okay, so this is our looking direction. If this is the image that is going to be formed in front of the focal point, we need, first of all, its resolution and its size. Okay, so this is the size of the this left L, R, T, and B are actually going to be given as scalars relative to the center of relative to our gaze. In other words, when I say L is equal to -2, okay, it means that the distance from this gaze towards left, this distance is 2 units. So from the gaze, from the center pixel, go 2 units in the -w direction. By the way, what is this direction I'm going? It's the -u direction, right? This was u. As you can see, this is u. If you go in the -u direction 2 units, that's the left boundary of the image. This is how we describe the boundaries. The boundaries, left, right, top, bottom coordinates, these are actually not coordinates. This L, R, B, 2. I mean, you may consider this -2 as the coordinate of the vertical line in the local coordinate system of the camera. Okay, if just considering the local coordinate system, this will be still the 0 point. Okay, I mean it's 0, 0 something. Okay, if you look at this point here in the local coordinates system of the camera, the x-y coordinates of this point is still 0, 0. Its z coordinate is minus something. Okay, its z coordinate is minus whatever the distance from here to here is. Its z coordinate will be so in other words, the coordinate of this will be 0, 0, 0 minus d in the local coordinate system of the camera. That's very important. Okay, so just sorry if this is confusing. We were talking about global coordinates and other things, but the global coordinates, world coordinates of this is not going to be 0, 0 minus d. It depends on what this I is. It depends on what u, v, w are. All right. I mean, it will be 0, 0 minus d only if e is equal to 0, 0, 0. Okay, that's the simplest camera setting. The simplest camera setting we are going to have is that, oh, let's have the focal point at 0, 0, 0. Okay, let's have u. Let's have the u vector as 1, 0, 0. Let's have the v vector as 0, 1, 0. Okay, look at this camera. If we have a camera like this, everything will be very simple. All the computations with the pixel coordinates here. For example, think about this. What is the pixel coordinate of this pixel 0, 0? We will just have to do very simple arithmetic to do that, okay? To find the pixel real world coordinates of this if the camera setting is like that. But we will show you methods to show in an arbitrary located focal point, an arbitrary orientation, arbitrary gaze vector, what will be the coordinate of this point. Oh, is there any reason? That's a very good question. Is there any reason not to have a camera always here? One reason is you may want the camera to move in the scene. You may have a fixed, for example, world coordinates set up. There may be houses, trees, in which you know the coordinate, their coordinates, and they're fixed. And you may want to fly through this town with houses and trees, and in that case, you will have your camera going over the entire town, in which it means that it's the global coordinate of your camera is going to be moving. It's not going to be always at 0, 0, 0. Now you can ask the follow-up question. Okay, why do we move the camera? Why don't we, if we want to do flyover, why don't we move the entire town over the camera? And we could do that in real life, right? I mean in virtual life. We cannot do that in real life. In real life, we move the cameras, but in a virtual world, we could actually be moving the town around the camera. And this is actually what, I mean, it will be something like that. I mean, these are just philosophically, practically, they will mean the same thing at the end. In other words, I mean, if you cannot find a way to move the camera, and if you find a way to move the objects around it, we will need to develop techniques to figure out what the coordinates of those objects be if I move the camera this way. Okay, they will turn out to be the same problem at the end. Oh, when you have multiple cameras and switch between them, that will be, I mean, imagine a smooth path that the camera is walking through. You will have to have thousands of cameras to switch between them. Right? And some of them, yeah, I mean, that will be very inefficient to have. Actually, having this multiple cameras, we will just indicate it by updating these values. Increment E by 1. Change the U vector to this. By making these dynamics, we will be able to do that. But for ray tracing, I mean, in order to implement ray tracing fully, we really need to solve this problem of given an arbitrary eye position, given arbitrary gaze, UV vectors, find the coordinate of this pixel. The world coordinates can also be moved, shrunk. For example, we will the linear algebra of these things, these transformations, is so remarkable that at the end, for example, if you want to move things, if you want to move the world coordinate or rotate the world, rotate all the objects in your world, or move all your objects, or scale all of your objects, these basic transformations, moving, rotating, scaling, we will be able to implement all of these with matrix multiplication. They will mean they will have the same operation on a matrix to form these effects. We will be able to merge those effects together. So that will come next. All right. But let's actually, we are out of time. I'm on Thursday. We are going to form the equation. So today it was just the basic overview of the ray tracing algorithm, what we try to accomplish. So the high level ray tracing algorithm is explained today, and we started doing some detailed computations, but we will the first detailed mathematics that we will face, finding given the ij pixel coordinates. So given ij pixel coordinates, then these pixel coordinates will be integers, okay, starting from 0, 0, going all the way to nx minus 1 and y minus 1. So we will have a certain number of resolution. Okay, we will have a resolution. And given these pixel coordinates, given the camera focal point, the distances, find the world coordinate point of the center of this pixel. After we have this coordinate of this pixel, what we will be doing is we will be generating our ray. Okay. So, are there any other questions? We will continue on Thursday, and I will post this video. I will post the links on OptiClass and call of this video today. Okay, there is another question. Yeah, the position and the image plane depend on world coordinates. Changing one over them should have no effect on the produced image. Actually, the world coordinate is the fixed entity. If you change the I point and the UV vectors, the effect will be dramatic. It's like you will be simulating moving a camera in a fixed world. Imagine this, my hand is in a fixed world. It has fixed world coordinates. If I change my eye, my camera around it, all the images I get of this hand are going to be different as you move the camera, as you change this focal point, as you change the these things. Okay, yeah, changing the local camera coordinates and gaze direction with respect to the world coordinates will make a difference. This is how we're going to produce these effects. And actually, we'll start some coding on Thursday, and we can try these things, and you'll see how the effects are going to produce different images. All right. Thank you, everyone. If there are no other questions, I will finish today's lecture and see you all on Thursday. Bye.